Welcome everyone, my name is Michele Portolan and I will be presenting our paper Security EDA Extensions for P1687.1 and 1687 callbacks. Before proceeding, I would like to acknowledge my co-authors from Team Laboratory in Grenoble, Vincent Reynaud, Paolo Maistri, Regis Leveugle and Giorgio di Natale. The presentation will start with a little introduction about 10 standards and their relationship with security threats, and more importantly, what is the impact on the overall test flow. We will then make a short introduction about what does it mean to extend EDA tools by providing the example of System Verilog DPI. We will then move on to present our modeling proposals for both 1687 and P1687.1 and how it is connected to security extensions. We will then draw some conclusions and present some perspectives for the work. So what is a test standard? The test standards always start from some user requirements, here in the bottom left-hand corner, where some users get together and issue a request for PAR to IEEE to be able to start working as a working group. This work takes a few years so that we can get to a draft that will then be submitted to IEEE for ballot, and if it is accepted, it will become our standard document, which will be used to obtain the EDA tools and the hardware implementations. Each few years, some 5-10 years, this might be reviewed to correct errors and introduce new features. Unfortunately, security threats doesn't wait for this long time period. You can have threats coming in matter of months or years, and you need to react to them as soon as possible. So you cannot wait for the next release of standards. You need some way to act now so that the threat is resolved. Solutions for possible threats to a scan-based system do exist. I will present two of them. One is scan encryption. The basic idea is that if you have here a system under test that is in a non-secure environment, you don't want to expose data directly on the stream, but you take your vectors that are generated by your standard compliant EDA tool and you pass them through some encryption phase so that the data that is exchanged is hidden. So a possible malicious user or an attacker won't be able to directly access the data. The problem is that this encryption is not standard compliant, so it cannot come from your EDA tool. You need some custom code that will take care of encrypting the vectors that need to go through the system and decrypt the vectors that come back. This means that you have one additional step in your flow, which might be a problem for debugging, or if you need some interactive way, or even if you are non-symmetric, so you don't have everything that is protected, but you need some part protected and some not. So this works, but it needs some custom code to make it happen. A possible solution for partial protection of the system is to take the parts of your system that need protection and you put them behind some authentication hardware. This authentication hardware might be something like a secure SID. So an SID will open only upon particular conditions. These conditions are defined by the security users and could be, in the simplest case, scanning inside secret key, or in more complex setup, provide a complete authentication based on the exchange of challenge and response protocols and the generation of session keys. This means that their actual implementation is even more complex than scan streaming. Why? Because your vector does not need simply to be wrapped, but you also need to provide some authentication sequence before, where you're putting in the challenge, receiving the response, and resolving if the response is correct or no. So your authentication software in the middle is doing even more complex steps, and your standard tool will be in a big problem of doing any type of direct access to your system. Once more, if you need to make some debug or some interaction, or if you have some, once more, non-symmetric setups where your authentication may change over time. So, to sum it up, what is the impact of the test flow? The EDA tool takes its strength and its added value from the standard compliance, because it means that we'll be able to support any type of solution that is inside the perimeter of the standard. Unfortunately, security threats comes much too fast for standards to be able to evolve and give them a solution. So, each time there is an important threat, the only possible solution is to have some specific workaround that will become between the actual EDA tool and the user. Too many of these steps means that you will have so many different standard steps that the user will lose sight, let's say, of the standard, won't be able to really exploit all its features, so you're basically losing all the advantages. Which it means that in terms of the real world, real adoption is quite limited, because there are two main priorities. For test, everything must work. You must be able to access your system. Otherwise, you won't be able to test and validate it. For security, you need the solution to work. And also, less is better. You don't want to have all these different custom things, because you won't be able to follow them, and you might end up to add more threats, more weaknesses that you are actually resolving. So, going to too many steps, you are actually ending up doing nothing. So, is there a solution to provide new functionalities without actually have to change everything in your software? The answer is yes, you can do it through what is called an extension. The extension is some interface, some flow that allows to provide new functionalities to one tool, but maintaining compliance to its specification, and most importantly, avoiding modification to its source code. This can be done in several ways. We will take one example from our field, that is the direct programming interface from System Verilog. What is this? The idea is that sometimes when you're making some test benches, you might need to make some really complex operations that are not possible using just pure System Verilog, which even with all its functionality still remains an HDL and not a full-fledged programming language. So what is possible to do thanks to GPI is to provide some hangs inside the System Verilog code that the simulator will be able to use to access some external codes that is written usually in C, that will be able to be executed, and so your simulator will be executing custom code that's been defined outside of it, and then we'll come back to its execution. This is something that can be used for a lot of applications. The most renowned is for UVM, Universal Verification Methods, where you can have complex routines that are defined through an external system, like what could be in MATLAB or whatever is your tool, and then are wrapped inside DPI, so that your RTL simulator will be able to execute these complex test benches without actually knowing what it is doing. This solution is done in two steps. The first, your System Verilog code has been abstracted so that the modules and the way they can interact with the external code has been defined in the standard document. The second part is the interaction with the external code is codified through a specific language API. In case of System Verilog, it's C. With these two elements together allows the inclusion and execution of external code. So, how are we going to leverage this principle for our solutions? We need, of course, start from a modeling of our system so that we can define what are the abstraction nodes and where these handles, or which we call callback, can be defined. The topology of a 1687 system is defined through the ACL representation. This language is mostly structural language that defines how the different elements are connected together. But if you analyze their behavior, you will understand that basically there are just three different types of nodes. You will have the register nodes where you can put data. You will have some linker nodes that will be the muxes that allows for the dynamic topology, so changing the size of the actual scan chain, and then you will have some chain nodes that allows for hierarchy. Then the difference, the novelty of P1687.1 is the possibility of going outside of the tab. So you will have some interface nodes that will be the access links that allows accessing the system under test, and then you can have one or more different adapters that will allow you to change this test access point. So how we are going to model these parts? First, we'll start from the linker. The linker is just a generalization of the Scan Mux. So a Scan Mux, what is its role? It will take one or more registers or subsystems that are behind it, and based on a certain register that is controlling it, will define which one is accessible at a certain moment. If we abstract it from a functional point of view, we end up defining just 3 possible operations on this linker, we will call it. So you can try and select one of these registers, you can deselect when you don't need anymore, and at a certain moment in time you might query the status of a linker to know which path is active at the time. This means that once we define these 3 functions, we can abstract them through a C++ API, write some custom code that is able to follow and realize these 3 functions, and we can provide it to our standard compliant EDA tool, which will be able to use and configure the topology for the standard scan linker or for more complex ones if we just change the code or what we decide to call a path selector. The interface, it's the new addition of P1687.1. So basically it's what allows you to go from the retargeting domain where you're going from a basic 1687 register to the whole chain to the transaction domain where you will have some operations. In the case of a 1149.1 tab, you might have several operations like the scan instruction register or the scan data register. In abstractions, this means that you will have some values, some vectors, retargeted vectors that are coming to one or more channels in your interface, and you will need to transform them to different type of operations. This is what in 1687.1 terms we call an RVF operation using this relocatable vector format. And once more, if we define this interface, we might be able to provide an API for a standard compliant tool that will take the code that implements these callbacks and be able to make the retargeting, so not the retargeting, sorry, the transformations from the retargeting to the transaction domain without actually knowing what is going on. So this is a generalization of the access link, and we need this API to make this transformation between the vectors and the RVF format. Once we get into the RVF domains, we can then have one of the biggest novelty of P1687.1, that is being able to move through different domains. So for instance, if after your tab you have a I2C interface that moves you to an I2C domain, then you might have some sort of interaction. In this case, I make a USB dongle that goes to the SUT. Once you got to the RVF domain, you can make all these different steps. So in our abstraction, each one of these steps, we call it a translator, where we have the callbacks that are pretty similar, that takes the RVF from one side and push them to the other side, and giving the translator code. Each one of these different translator will be described and usable by the standard compliant EDA tool, which will know absolutely nothing of what is going inside of them. In order to use this type of abstraction, you need to have some domain-specific language, so DSL, to describe it. We may consider that the C++ API is already been defined, so we don't need to express it in our DSL. Similarly, the 1687 connectivity is already done in ICL, and for what is the interfaces and the translators, you will have already functionally validated them through simulation or RTL, so once more, we don't need to describe how it works. We just need to describe how it can be used by making some pointers to the different protocols that need to be loaded and provide dependencies. Now that we made this modeling, how can we actually use it to express security extensions? Well, it's actually pretty simple, because thanks to this abstraction, security is just business as usual. If you have a stream cipher, you just change the flow of packets, of RVF packets, so you can describe it as a translator and provide the code to your tool. Similarly, your authentication step is just a particularly complex Scan Mux, so a particular linker, which you can describe your code in terms of the API and provide it to your tool, which means that everything is completely transparent from the user, which is not seeing all the complex part of the security that is behind, and is able to use all the features of the standard that are provided by the tool. Moreover, as each one of these steps is inside this modeling, you can compose them freely and have a complex system that takes advantage of all different parts without taking the difficult parts that are the adaptation of the workarounds. To validate our proposal, we took this extension paradigm and implemented inside our MAST tool, which is a retargeting dynamic engine for both 1687 and P1687.1. And we combined it with some pre-existing solutions for authentication as an SSAK controller and for encryption as a trivium cipher. This means that we took the SSA controller and expressed its C++ implementation as a plugin for a linker. We took the trivium implementation, which was some Python code, as an extension for the protocol and the translator. Then we used another translator that provides interface with an RTL simulator to make co-simulation with ModulSim and BCS. We were therefore able to freely execute interactive PDL code with any type of combination of these different solutions. For the sake of time, I won't be able to give you here a demo of this solution, but you can find a full demo in the YouTube channel for TimaLab, which is here. So, what are the conclusions and the perspectives of this work? We show that test and security are both really important, but they have different time frames. So, it's difficult to be able to combine the two. In the same way, 1687 and P1687.1 provide means of going beyond traditional scan, and we decide to exploit them to provide these new EDA extensions. This means that security is not a special case anymore, but is yet another extension, like everything else, we can use in a flexible, open to evolution, and most important, standard compatible way. And we validated it thanks to a real implementation with our MAST tool. So what remains to do? What we showed is one solution, but it's not the solution. The next step forward will be a standardization, so decide which actually will be the API inside the standard P1687.1, and I mentioned the RVF format, but which will be its exact specification. This is the work that's been ongoing at this moment in time in the P1687.1 working group, and you will have a presentation about its status later in the same session. So, thank you very much for your attention. I hope that even in this virtual solution we will have some interesting Q&A session. Thank you very much. To validate our proposal, we implemented